In today's discussion, we will further touch upon the aspects which we did not cover earlier. As you will recall, we had talked about an automata that the inference machine of a rule based system executes, and it consists of 3 states or 3 phases. First is the match phase, where the rules are compared, the antecedents of the rules are compared, antecedents, or later on we will see that we can also compare the consequence, but for the sake of simplicity for the time being, let us assume that the rules and the conditions of the rules are compared with the existing facts in the fact base, and if there is a match, the rules whose antecedents match are triggered and they are fed to the conflict resolution strategy. In the conflict resolution strategy, we select a subset of those matched rules and feed it to the execute phase, and in the execute phase we fire those rules, and as a consequence of firing these rules, the new facts are generated and the fact base gets updated. We go on carrying out this activity till either the goal is met or there are no more rules to fire. Today, we will start our discussion on the conflict resolution strategy. You should also recall that we had said that the exploration of the execution of a rule based system is equivalent to exploring a search space. All right. So, there we can think of a search space consisting of nodes and arcs which are created, and different rules that are being fired are equivalent to traversing a particular path of that search space. Now, which rule to fire is determined by the conflict resolution strategy. Therefore, conflict resolution strategy is a key factor in the execution of rule based systems. So, today we can see that the conflict resolution strategy, its objective is to decide which of the triggered rules in a particular state, stage should be fired. All right. We can use different strategies like the first come first served, rule ordering, specificity ordering, etc. Now, say what is meant by the first come first served strategy. Let me try to elucidate this point. When we have got a number of rules, then the rules are ordered in some way. Some rules are written first and some rules are written later. All right. Now, the conflict resolution strategy, if it is first come first served based, then it will select just the rule out of the triggered rules, the rule that appears first. So, if you have to give some priority to the rules, then the rule writer or the rule designer should write the rules in the proper order of priority, because here the conflict resolution strategy is rather simple. It does not do anything special, it just selects the first rule to fire. On the other hand, the other strategy, which is known as the specificity ordering strategy, is different. It is different in the sense that it will select the rule that is more specific. Let us consider a scenario, say if A then X. Another rule says if A and B then X. Okay. I repeat, if A then X, where A is a predicate, then X, and the second rule says if A and B then X. Now, which of these rules are more specific? So, assume that both the facts A and B are true and are there in the fact base. So, both these rules are triggered. Now, which rule is more specific? obviously the second rule is, that is, if A and B then X is then Y, sorry, consider the rules like if A then X, if A and B then Y, all right. Now, what should we conclude, X or Y? Both A and B are true in the fact base. We should, our common sense tells us that we should infer Y, because the rule if A and B then Y uses more facts which are known to be true, all right. Suppose there are two rules, if it is Sunday it is a holiday. Another rule says, okay, if it is Sunday or, for example, it is summer vacation, then it is holiday. Now, whenever we know more facts, in that case that rule is more specific, because it is using more information. So, in the specificity ordering the rule that is selected is based on the rule which is more specific, that means whose more number of antecedents are matching. Then other rule is fire all. Fire all means whichever rules are enabled will be selected, will be fired. If there are 5 rules enabled, those will be fired. The other strategy is heuristic measure. Heuristic measure, as we are discussing in the last lecture, heuristic is based on partial information about the domain, and it also can use some of our general knowledge, some of our past experiences about solving some problem, about a particular scenario. So, if there are multiple paths to the goal, we should select the path that is more probable to lead me to the goal. For example, let us say I am in this state, all right. I do not know what is happening. Suppose I am in this state, a particular state S1, and my goal can be in maybe here. This is my goal node, all right. Now, there can be different rules which can be fired, all right. Say if I fire rule R1, then I will follow this path. If I fire rule R2, then I will follow this path, and each of these firings will take me to different states. Now, maybe again from this state I will have another rule to fire R3, and from here another rule R4, which will lead me to the goal. Whereas, from here there is a possibility that I will fire another rule R5 and I can reach the goal. So, when I am in this state S1, obviously, when this R1 and R2 are in conflict, these two are in conflict, which one should I select? If I sit over here and look at this state and can also find out which one of these rules are, or at least not find out, at least if I can guess that which one of R1 or R2 will bring me closer to the goal, then that can be used as one of the strategies for selection. It is not the case that always it will be it will lead me to the minimum path or the shortest path or the least cost, but we have got no other way but to guess. We have to guess at particular times, and based on that we have to make a decision. Say suppose I have got some block here A, B and C. These are 3 building blocks which are kept in this way. Now, this is my start state, all right. This is my start state, and I want to arrive at a goal state which is something like this. I should have A and on that B and C might be here. Now, from here if I can move C either, suppose one possibility is move C to table, which will lead me to a particular state where it will be A, B and C. There could be another move, that is another rule, which can say that move C on B. In that case, that will lead me to a particular state which will be A, B, C. Now, which of these two states, this one is one candidate and this is another candidate, which one of these two states will bring me closer to the goal state? Obviously, this one, because in order to move B on top of this, B's top of B must be free, then only I can straightway move B and bring it over here. If I go to this state, then I need one more step where I should bring down C and free the top of B. So, this state is not as close to this goal state, this is the goal state, this is not as close to the goal state as this state is. Therefore, if I have some strategy by which I can see that okay, this rule is resulting in a particular state which does not have the top of B free, my heuristic is this, that in order to move B, it is preferable that if the top of B is free, it is preferable, otherwise I have to make the top of B free, and that preferred situation is being brought in by this rule. So, obviously, in a heuristic measure, if I have got a heuristic strategy, this would be a better choice and this would bring me quicker to the goal. All right. So, that is what we mean by heuristic measure, and that is somehow the distance to the goal. We have to evaluate the distance to the goal in some way, and in what way, that is very much dependent on the problem that we are solving. In the blocks world example that I have just now given, we are looking at how close, how easy it is to move a particular block that we really desire to move, but maybe in some other scenario the costs or the measures can be different. All right. For example, you want to make a travel from one particular city to another city. In that case, and you also want to minimize the amount of money that you spend, and also you want to minimize the time. Now, how do you do that? Suppose there are 3 routes, obviously walking is one possibility, another possibility is by bus, another is by air, maybe by train, etc. There my heuristic measure will be a little different. For example, if I am in this city, say A, and I want to move to this city B, and I have got possibilities of going to city X, then city Y, and then from here to this. So, there is a bus route here, all right, sorry, this is bus, all right, and there is one train which brings me to city P, and from there is another train which brings me to city Y, and from there I have to take bus, all right. Or there may be another way that from here I can also take a train to B. Now, you see my objective, my goal is to reach B. Now, when I come to this city P, suppose I at this point I decide that okay, right now I have got enough money, but my time is really an issue. So, I will come over here. Now, when I am at this point, then I have got two choices. Either I take the train from here, this train, or there is a direct train, but this train if I take, then I will have to take the bus again. So, here I find that okay, I have got say some x t amount of time left, t is the time that is left. Okay, I have to reach within that time, and say c is the cost that may be paid. All right. Now, I have these two parameters, and sitting at this point I have to make a decision. Now, obviously, I can see if suppose this is very important, that this is very time is very strict criteria, then from here probably I will not think so much of the cost, and I will take this because this is a faster train and it will go directly. But depending on this time that I have, if I have enough time, I may prefer to go by a cheaper local train and then take the bus. So, for this at this point I will have to compute a cost function that will consist of some parameter, some weight of the time left plus might be, this is a very simple expression that I am writing, to the cost that has to be paid. So, some sort of function I have to compute sitting over here. So, this the cost function can be varying for different problems. So, depending on the cost function, I will be selecting a particular path whichever satisfies my need better. Okay. So, I hope you have understood what is meant by heuristic functions, and I am sure this you have also come across about when you learnt about the A star algorithm, where you have looked at the heuristic measure, okay, heuristic function. The other strategies that are used for this purpose are refractoriness. Now, this term means that rules which are once fired will not be fired later. We have seen this in the earlier lecture. Okay. That is one thing. Another very important approach is to use meta rules. What is meant by meta? Meta knowledge means knowledge about knowledge. So, it is another level higher. So, meta rules encapsulate, meta rules are rules which encapsulate the knowledge of how to use rules. So, whenever there is a conflict, we use a set of rules to resolve that conflict. Such rules are known as meta rules. So, rules about these rules are embedded within the inference machine that provide the information about which of the rules apply under which condition. Now, when we look at now execute phase is just taking the decision. Now, the performance of an inference machine for a rule based system is very much dependent on the match phase and the conflict resolution phase, but as regards time 90% of the time is spent in the match phase, and rule based system designers have taken different measures of translating implementing rule based systems in using different data structures which minimize the match phase. All right. But just remember that match phase is a very important parameter, and very interesting algorithms like Reti match algorithm and other techniques have been invented which minimize this overhead of matching. So, the performance of a rule based system is very much dependent on that. However, now I would like to emphasize on this point time and again that what we really do in a rule based system is searching a particular space. We just try to search a particular space. I prefer to always present this sort of diagram. Say here we have a start state, and there are different paths through which I may go. Now, there are might be my goal node is here. This is my goal node where I want to reach. I can reach that through different paths, might be through these paths, or maybe there is a shorter path, whatever. Now, all these are just like the trees, all right, that we had drawn earlier. So, we have to search this space, and so assuming that the goal is there within this search space, we have to find it out. Now, in the case of a rule based system, how is the search space defined? How is the search space defined in a rule based system? Let us see. I can say that, say A B C implies D. So, in this diagram I am just drawing the consequence as squares and the antecedents as circles. There may be another rule D G is giving rise to might be P, and there is another rule which says P, and this is AND, okay. These links are AND links, P and A and B and C, D and G, P and might be B is leading me to Q, and Q is my goal. Now, I may have in my fact base initially A is true, B is true, C is true, and G is true. Suppose that is my starting scenario. Now, obviously, A, B, C being true, I first check this and check this. So, this rule fires. So, as soon as it fires, this fact D is added to the database. So, it is D. Now, as soon as D is fired, I can look at D, D and G is also true. So, this rule also fires, and this adds P to my fact base. Now, P is true and B is true. So, I arrive at the fact Q, which is the goal, and so my goal is solved. That is one particular way of looking at the whole thing. So, what is happening in this case? In this case, I am starting with my given facts and trying to infer new facts. And in the process of inferring new facts, I first infer D, then I infer P, then I infer Q. In the process of inferring these facts, I arrive at the goal. This is one way of looking at it. Otherwise, I could have done it in another way. I could have, since I know Q, I could have started from Q. How? Say my objective is to prove Q, and what were my rules? If I recollect properly, A and B and C generated D, D and G generated P, and P and B generated Q, all right. And my fact base was having A, B, C, G initially. So, now, but here I look at the problem in a different way. My objective is to prove Q, I have to prove Q. Now, I can also look at, till now in our discussion, we are continuously saying that we compare the fact base with the rule base. Now, suppose I start to look into the rule base and see, well, here there is a rule which has got Q as its consequent. Now, when is Q true? Q is true if P and B are true. So, if I can prove P and B, then obviously Q is true. So, this is my goal, and in order to prove Q using this rule, rule 1, R1, R2 and R3. So, using R3, what I can do is, I can see that using R3, I am having two different goals to prove, one is P, another is B. Now, as soon as, so what I have created is a set of sub goals, that means, if these two goals, if these two things are proved, then Q is proved, that is my objective is reached. So, these are the sub goals. So, starting from a goal, I generate a sub goal. Now, I can immediately I look at, are these already true? I can find, well, in my fact base B is true. So, this is proved, but this just being proved does not prove Q, I have to prove P also. So, the sub goal that I have to prove now is this one. Now, in order, then I look at the rule base and find out which rule can help me in proving P. I find, well, this is the rule that helps me in proving P, and how can I prove that? If I can prove D and G. So, I create another set of sub goals D and G, which I have to prove. Again I look at the database and find, well, G is proved. My only problem is with D. Now, is D true? How can I prove D? I look at, go to this rule and find out that well, there is no space. So, I am just well, I can manage with this A, B and C, these have to be proven, all right. I can say, I am just removing these rules for the time being. So, I can say that D is proved if A is proved, B is proved and C is proved. Now, I can, luckily I can see that in my database A, B and C are both true. So, this is proved, this is proved, this is proved. Therefore, D is proved and G is proved already. So, D and G both being proved, P is proved, and P being proved and B being proved already, Q is proved. So, what I have done in this case? In this case, I have started with the goal and tried to prove the goal by generating sub goals and proving the sub goals. Okay. So, there are, we have seen two distinct ways of searching the space. So, let us look at it here. Now, the example that I have given must have made it clear. We start from the given facts and try to arrive at the goal. That is the first thing that we did. We started with A, B, C, and A, B, C, as soon as I saw A, B, C, I could derive D, and since D was there and G was also true, I could derive P, and since P was there and P is proved and B is there, I have proved my goal Q. That is one way, that starting from the given facts and try to arrive at the goal. The other way, the second one that we did is we started with Q and we tried to prove the goal using the given facts. We tried to prove Q and we found that Q is true if P and B are true. So, our next job was to prove P and B. We have seen that B is already true, but P was not. So, we then searched for how we can prove P. We found a rule that P is true if D and G are true. Now, G was already true. Now, how can we prove D? We found a rule which has got D in its consequent, okay, and in order to prove that, therefore, in order to prove D, we had to prove A, B, C. So, in that way we proceeded. So, this is another way that where we start from the goal node and try to prove the goal using the fact. Sometimes this approach, the second approach, is known as goal driven search, and this first approach, starting from the given facts to arrive at the goal, is known as data driven search. Now, we will now concentrate on these two reasoning mechanisms that are used in rule based system. The first one is forward chaining mechanism, that is the data driven search. We have already explained it, but still let us look at it. Starting from the start state, we apply the rules one by one to arrive at the goal state. As I have said, this is also known as data driven search. Now, forward chaining may lead search to a dead end. Okay? We may reach a dead end because we might have arrived at a particular point we have arrived at a set of particular facts which does not lead us to any further exploration of the rule space. In such cases we need to do backtracking. Backtracking can be chronological or intelligent. Let me explain this again. Say I have got a rule A and B leads to C, X and Y leads to P, and P and Q leads to G, which is my goal. Suppose these are 3 rules, and suppose in my fact base I have A to be true, B to be true, and X to be true, Y to be true, and Q to be true. Suppose this is what is there. I am just taking a very simple scenario. Now, according to the rule based system that we know initially which are the rules which are triggered. This rule is triggered and this rule is triggered. So, I am in the start state and I have got 2 rules to fire, rule R1, say this one, R1, there is some problem, I am just writing it here again. A and B and C implies P, sorry, A and B implies C, X and Y implies P, P and Q implies my goal, this is G. Now, the facts that we have are A, B, X, Y and Q. Now, this is my first rule, this is my second rule and this is the third rule. Now, when I start with my start space S, we start with the start node, I have got rules 1 and 2 both enabled. So, this is enabled, this is enabled. So, I had 2 possible paths, but somehow I selected path 1. So, I have come to C. Now, with this I can see that I cannot proceed any further with this new fact. C has been added, but if my strategy is that always select the rule or just fire the rules which with the newly generated facts, then C does not lead me anywhere. I cannot proceed further. Therefore, at this point I have to do backtracking. I have to go over here and look at the other rule that was left to be fired. So, I fired this rule, I get P and then Q was true. So, from there by firing rule 3 I can get to the goal G, but this was a dead end that I had reached and therefore, I had to backtrack and see which are the rules to fire. Now, usually as you must be knowing from your data structure or algorithms class that backtracking usually goes one level up from any tree, all right. So, in general what happens is that whenever I have a tree, like this, which I am exploring in either way, when I am here, suppose I have reached some dead end here, then usually we backtrack one level up and look at these points, look at the other possibilities and try over here in a typical depth first search. Now, if I find a dead end also here, then I go up again here and I find that there is no further way of exploring here, then I go one level up and try to proceed this way. Now, this is called chronological backtracking. But there is another way which artificial intelligence techniques can use, that suppose I have looked at I have found a dead end here and I sit back here and think of why, what happened really, which has gone wrong and which does not allow me to proceed any further, or some particular thing that I wanted to deduce has not been deducible. If I can analyze the domain, then might be I can straightway go to a particular node which would have given me a better chance of reaching the goal. That sort of intelligence, if imparted in the search strategy, gives rise to intelligent backtracking. Otherwise, normally what we carry out is chronological backtracking. All right. So, in forward chaining system, the facts are held in a working memory. All the time that we are drawing a fact base, that is kept in a working memory, and condition action rules which represent actions are in the form of if condition and then action, and typically the actions involve adding or deleting the facts in the working memory. All right. And the control cycle that we have talked about is recognize act cycle. This is exactly the same which we discussed in the last lecture with match. Match is the recognize, then resolve the conflicts and act, that is the execute phase. So, what we do over there? We find all the rules which have satisfied conditions given the facts in the working memory. We choose one using conflict resolution strategies, perform actions in conclusion, probably modifying the working memory until no rules can fire, or we halt, that means or the goal has been met. Now, so here is an example, the same example that we did in the last lecture. Here we can do it in the forward chaining mode in this way. We first look at this and look at these rules and these facts. We can find that okay, hot, this one does not fire, this one is firing. If alarm beeps, then add smoky. So, we add smoky over here, and then we find out that this rule is matching. We can fire this rule and add fire to the database, and then we can find out this rule to be enabled, and we fire this rule and we arrive at the conclusion, switch on sprinklers. So, typically the examples that we are giving till now were forward chaining based. Okay. So, this is the same example that we had talked about. So, here as I was explaining, all the rules that satisfies the condition in that case was just the second rule, and so we added smoky and the working memory got changed. All right. So, ultimately we arrived at switch on sprinklers. Now, forward chaining systems are very useful and have been used as a model of human reasoning, and there are various expert systems. We will discuss little bit of expert systems today, which have used this sort of reasoning. There is a forward chaining mechanism, and these are also they essentially use pattern matching. There are different languages, there are different tools which are available to build such rule based systems. So, here is an example of CLIPS. CLIPS is a system which allows you to quickly build a rule based system. Here there is a language like define rule, fire alarm. So, here that particular rule is written in a particular syntax. The rule that we are showing has been given a name, fire alarm. Now, here what it means is that this part is the antecedent part and this part is the consequent part. If the temperature is hot and the second bracket means the and the environment is smoky, in that case assert fire in as a new variable. So, quickly let me just talk about the working memory thing that we are talking about. So, we have got a rule base which consists of the rules, and there is a working memory. working memory, which is also known as short term memory by some. All right. And so, in this working memory only the information relevant to the particular problem is stored. But in general, we can have some more facts which are not specifically relevant to the problem, but are more general. For that, often in many systems we also have a long term memory. Okay. So, in those cases we often have a long term memory. The rule base is also related to long term memory. So, we can have long term memory and short term memory. Now, this long term memory is storing some facts which are in general true. Now, sometimes they are already captured in the rule base. So, often we do not make a distinction between these two. All right. In that case, we consider this entire thing to be the long term memory, LTM. Now, so might be, let me give an example. For example, we know that the sides, two sides of an isosceles triangle are equal, or all the three sides of an equilateral triangle are equal. I can write that as a rule in general, that if a triangle is isosceles, then all sides equal. That can be kept as a rule, and specifically when I give PQR a triangle or ABC a particular triangle, whatever inferences we do about that, that is stored in this working memory, and the inference machine also looks at this rule base from this working memory. So, the inference machine is sitting over here, which is looking at the working memory and the rule base. The facts are added to the working memory and deleted from the working memory. Okay. So, about this working memory, we are till now saying that it is a fact base, but we also we mention it as a working memory. Now, we come to the other mode of reasoning, that is a backward chaining. In the backward chaining, you can see that the same thing we can do, the same problem about that sprinkler on or the fire, smoke, etc., we can deal with using backward chaining. This allows a more focused style of reasoning, because in the forward chaining, as we have seen in that example, we can often, if our inferencing mechanism is such that we generate a particular rule, we fire a particular rule to generate a particular fact, which will not be useful for proceeding further. That sort of scenario is very much occurring in the case of forward chaining. On the other hand, backward chaining is very much goal driven. We know that which particular goal to solve and we can proceed accordingly. Therefore, often it is said that backward chaining is more focused, but often in many cases we will find that forward chaining is also very useful. I will just give you two specific examples. When we are trying to design a system, we are constructing something, when we do not have an unique solution, there can be different ways. You are designing a motor car, you are designing a house on computer. So, therefore, you have got different choices and you can make a particular selection and proceed in a particular path, you will come with a particular design. In such cases, forward chaining is very useful, given what you have at your disposal, what are the things that you can conclude. On the other hand, the other class of problem, another class of problem if we think of, is the diagnosis problem. Somebody is having headache. Now, why does he have headache? So, if there be a rule, if the person has fever and typhoid, whatever, the doctors will be able to tell better. If there is a rule that if he has migraine, then he has headache. So, if headache, then we can check whether he has got migraine or not. Then what is the test for migraine? Say if x and y, then migraine. So, in that way we can proceed. So, for diagnosis or even for fault diagnosis in any machine, we look at a particular thing that has happened, we try to find out, prove that why this has happened. Okay? We try to explain why this has happened, or we often try to prove whether what we are suspecting to happen is indeed the case. In such cases, backward chaining is more useful. So, you can see here that we, in this case, we start with a possible hypothesis. So, let us play with the same example that we did just now. Suppose my problem now is, should I switch the sprinkler on? Suppose I set this. Earlier we had hot, okay. We tried to see whether there is a fire. If there is a fire, then only I will put the sprinkler on. Here I am posing the problem in a little different way. Here the problem is, should I put on the sprinkler? When should I put on the sprinkler? So, we set this as a goal to prove whether I should put up this sprinkler. So, the basic algorithm, as I have explained little earlier, is to prove a goal G. If G is in the initial facts, if G is already known to be true, then the proof is done. Otherwise, we have to find a rule which can be used to conclude G and try to prove each of the rule's conditions. Okay. So, in this case, again we look at this example. Now, I am trying to prove switch on, whether I should switch on sprinklers. My fact tells me that alarm is beeping and it is hot. Then I first check, I should switch on sprinkler if there is a fire. Is there a fire? I do not know. So, I will go to this rule, all right, and try to find out, is it hot and smoky? Now, I can find it is hot, but is it smoky? Then I have to see whether the alarm beeps. If the alarm beeps, then obviously my goal is proved. So, once again quickly let me work it out in the way of a search graph. So, here my query is whether the sprinkler should be put on. Now, sprinkler should be put on. My rule R3 told me that if there is fire, if there is fire, is fire true? Fire is true. My rule R1 is telling me that fire is true if it is hot and smoky. Now, hot was true, but is smoky true? Hot was given in the database. Now, is smoky true? There was, my rule R2 told me that if there is an alarm, then it was smoky. Now, alarm was true, so smoky was true, so there was a fire, so I should put the sprinkler on. So, look at my conclusion, the way it has gone. This is backward chaining. I started with a goal and generated sub goals, and I tried to prove each of the sub goals, and the truth I propagate in the other direction. All right. So, backward chaining example that we have just now worked on is switch on the sprinkler. It was not in the initial facts. Had it been in the initial facts, my job would have been done, but it was not there. So, we arrived at different facts. We created new goal to prove whether it is fire, that was also not in the initial facts. So, I had to check whether it is hot and smoky, and in that way we proceeded and found that the goal was alarm beeps, which was true. So, therefore, we proved on the sprinklers. Okay. Now, rule based systems are very much used for a type of systems which are called as expert systems. And now, whatever has been written over here, I would like to do a little bit of correction. These are not expert systems, these are expert system tools. There are what are expert systems? Expert systems are the systems which attempt to solve the problems such problems which do not render themselves to ready solutions through algorithmic means. So, where we really need some experts knowledge, for example, the job of a doctor, okay, where we really need domain specific expertise, we cannot always really write a program and find and diagnose a particular patient. All right. So, often expert systems are mostly, in many cases we have seen that expert systems are rule based. All right. There are different ways, often those are rule based, and an expert system consists of the knowledge that is encoded in the form of rules, in case of a rule based expert system, in the form of a rule to demonstrate some sort of expert behavior. And in order to facilitate development of such rule based systems, we often need to utilize some tools which facilitate our development of such rule based systems. So, CLIPS is one such system. There is a language which many of you must have heard of, is Prolog, which is programming logic. Now, Prolog is a specific case of backward chaining. That means, Prolog utilizes backward chaining method of reasoning that we have just now discussed. CLIPS on the other hand uses forward chaining. So, we will just briefly mention about expert systems, that is systems acting in a particular domain and behaving like, it is a tall claim though, that behaving like human experts, it is not, that is the aim, to behave like human experts, but that is not absolutely possible as yet. But in some specific cases where there are mundane things, where the skills are very important, the skills of the human beings. I mean, think of a workshop scenario, there are people who have worked on some particular trade and they can immediately recognize when a particular fault occurs, where the fault has occurred. Suppose a motor is rotating and there is some peculiar sound somewhere, they can immediately pinpoint. Now, one model of human reasoning says that these expertise can be encoded as set of rules, and if such an expert person retires, often the youngsters who join the company do not immediately get that expertise and cannot show so much performance. So, if their expertise could be encoded in the form of such rules using some tools like CLIPS, Prolog, whatever, if such expertise could be packed in and the rule based system could be used, then that could be useful. So, in that sense expert systems are useful, and there are quite a few expert systems which have made some impact to researchers, and in some specific cases to some companies like Boeing, General Motors, where expert systems are really being used in industries. So, expert systems are applied to problems for which no algorithmic solutions exist, and this is now an expert system when we design cannot be an all purpose expert, a panacea. It cannot even match the expertise of a human expert who can be a very good automobile diagnostic person. At the same time he can talk of might be drama or something. So, his domain is much larger, but when we talk of expert system in this context, we are talking of a very narrow domain in which we have just been able to put in some rules to demonstrate some expert like behavior. That sort of system is really finding its use nowadays, and This has been widely used in medical systems, where we start with a set of hypotheses on possible diseases and try to prove each one by asking additional questions of user to the user. And one typical such system is Mycene, which is considered to be as one of the pioneering expert systems. We will come to Mycene later on when we talk of uncertainty management later during the course of this lecture.